All right, we are recording. Let me pull up the slide. Okay, all right, let's get started. So welcome to lecture 3. This is the lecture that we've recorded in advance. Just a few brief announcements. So first off, homework 1 is due today. It's due at 1 p.m. I checked online and most of you have already completed it. But for those of you that have not, hopefully get that done before 1 p.m. I'm going to assign homework 1, homework 2. I have a typo here on my slide. Actually, it's homework 1.2. So you all have done homework 1.1. 1.2 is going to be due, or is going to be assigned today to be due Monday. In that homework, we'll cover some dimensional analysis, the stuff that we didn't cover on Wednesday, as well as a little bit of math review, primarily trig. I did want to mention an announcement that came via email. I believe it was yesterday. It was either yesterday or Wednesday. I can't quite remember. But Marshall's offering virtual learning hubs for those of you that need a designated area for your virtual classes. For instance, maybe you're having Wi-Fi connectivity issues and whatnot. You go to marshall.libcal.com/reserve/VHUB. It's here on the slide. If any of you are interested in that information's here, and I've posted these notes to Blackboard as well. Okay, so what I want to cover today is I want to get back to that dimensional analysis that we talked about last time and see if we can work through that problem. And then I want to just conduct a real brief math review. I'm going to talk a little bit about algebra and a little bit about calculus, but really what I want to focus on is the trig, because trig is something we're going to be using very quickly when we start looking at vectors, particularly how to add vectors and how to determine resultants. We'll need to understand a fair amount of trig on the onset in order to accomplish that, so I want to talk about that first. But let's go back to our dimensional analysis problem. This is where we left off last time. So last time we were talking about units, and we were talking about really 2 tasks that we need to deal with units. One, being able to convert from one unit system to another, which is what was the focus of the problems that we did in class last time, as well as your homework assignment. But also whether or not formulas and expressions are dimensionally consistent. I'm currently teaching statics, but I teach some of the upper level courses as well, like reinforced concrete design and structural steel design and what have you. And with many of those classes, this stuff still can be a challenge even on the later courses. So I want to make sure that everybody's comfortable with doing this type of analysis. You're going to be dealing with a lot of formulas in engineering where you're going to be plugging and chugging values into an equation. If those values aren't consistent dimensionally, it's going to cause problems. So the best way or the best example that I usually give is what do you get when you take 2 apples and add to that 3 bananas? Well, it's not 5. 2 plus 3 equals 5, sure, but 2 apples plus 3 bananas just equals 2 apples plus 3 bananas. You have 5 objects, but it's not 5 apples or 5 bananas because those aren't dimensionally consistent. You can't really add apples and bananas in that fashion. If you had 2 apples and 3 apples, you could add those together and get 5 apples, but turning that value into a 5 really wouldn't make sense from an apples or banana standpoint. And that's a silly example, but we see this a lot in engineering. I want to go back to this example that we ended class on last time. This is looking at a fluid conduit, and so this is you'll see this in fluid mechanics. This is a portion of what's called Bernoulli's equation. Bernoulli's equation is a very fundamental expression that you use in fluids, and what it does is it quantifies the amount of energy, or what we call a head in fluids, the total amount of energy in a specific fluid conduit. And you get energy in a fluid conduit. So by conduit, you could think pipe, like a pipe with fluid in it. You get energy from really 3 different places. You get it from the pressure head, the velocity head, and the elevation head. And so you see these 3 terms in this expression, P over gamma plus V squared over 2G plus H. those terms are represent the total amount of energy. And so if I'm going to add those terms together, they have to be dimensionally consistent. So I want to look at these terms, and I want to see if that makes sense. So I have here on the left the terms that we're looking at. So I have pressure. Pressure I'm going to express, and so we're working in SI units in this problem, so pressure is going to be in Newton per square meters. We have a shorthand name for that in engineering. We call that a Pascal. So if you ever hear the term Pascal, that's just a Newton per square meter. So we have newtons per square meter. We have the fluid unit weight, so that's how many or how heavy the fluid is per unit volume, and so we express that in newtons per cubic meter. Then we have the fluid velocity in meters per second. We have the acceleration due to gravity, so that's in meters per square second. And then we have the elevation, which is just in meters. And I want to do a quick dimensional analysis to see whether or not this expression is dimensionally consistent. So let me stop my share real quick. And I'm going to share the entire screen. We're going to have that cascade effect again, so bear with me. There's that cascade effect again. So let me pull up the screen. Okay, and so here's the problem that we were looking at. I'm going to get my keyboard out of the way and lay my screen down so that I can do this problem. And so here's the formula, and here you can see each of the terms that we were looking at. And what I want to do is I want to take this formula and I want to start to expand it a bit. So let me get my pen out here. And let's do some computation. So I'm going to rewrite the formula. So we have P over gamma. That's that Greek letter, lowercase gamma. We tend to use that letter a lot in engineering for unit weights and all sorts of things. Plus V squared over 2G plus the height. Now, what I'm going to do is what's called a dimensional analysis, and hopefully you did this in your engineering computations class, but even if it's been a while, what I'm going to do is I'm going to replace these terms with the appropriate units. So for pressure, pressure is going to be in newtons per square meter, and on the bottom, this term gamma, this is newtons per cubic meter. Okay, so just so you're following here on the screen, this fraction here is just that fraction. Plus, okay, and now we've got this fraction here. Now we've got V, and so V is meters per second squared divided by, and then I've got 2G. So first off, let's do the G. So G is meters per second squared, like that. And then we have the 2. Now, what I'm going to do for the purposes of a dimensional analysis is I'm actually going to neglect that 2. And I'll tell you why. So let's say that I put the 2 there. Well, let's look at it this way. Let's say that you had a distance of 6 feet. Okay? Now, so just imagine in your head a distance of 6 feet. And you take that distance of 6 feet and you divide it by 2. Well, what is 6 feet divided by 2? It's 3 feet. It doesn't change dimensionally. If I take 6 feet and cut it in half, I'm still left with a dimension that is measured in feet. It only changes dimensionally when that 2 has a unit that's attached to it. So for instance, if I have 6 feet and I divide it by 2 seconds, well, the number is 3, but it's no longer feet. It's feet per second. Okay. So from a dimensional perspective, that 2 really doesn't matter, so I'm just not going to worry about it for the purposes of this problem. I could put it there, but again, meters divided by 2 is just meters. And then, okay, and so just to make sure everybody's following along, this term here is that term there, and then we add meters. And so that is that. Okay. So I've got these 3 fractions, and what I want to investigate is whether or not these fractions add up consistently. They have to make sense in a dimensionally consistent fashion. Okay. So let's see if maybe we can give ourselves a little bit of room here. We'll scroll down a bit. Okay, so we got a little bit more room. Now let's go back to some rules of arithmetic and some algebra rules, if you will. So first off, if I look at this first expression, basically what I'm saying is I have newtons over meters squared divided by newtons over cubic meter. That's what that first fraction is saying. I've got a fraction divide another fraction. Same thing here. I've got meters per second squared divided by, or sorry, meters per second, the quantity squared, divided by meters per second, the denominator squared, plus meters. Okay. And you should remember this from arithmetic, that if you are dividing two fractions, it's the same as flipping and multiplying. So we have Newton per square meter times meter cubed per Newton. So I just flip and multiply. Plus, and now let's take a second here with this term, okay? So if we look here, I have this fraction here, meters per second, but the quantity is squared. So what I'm going to do when I draw this down here is I'm going to say meters squared per second squared. I'm going to square both terms. Remember that from arithmetic. If you have a fraction and you're squaring the entire fraction, that means you're squaring the top and the bottom. And then multiplied, again, flip and multiply, second squared per meter plus meter. Okay. And now when we look at this, we can see that we've got a lot going on here that is going to simplify greatly. For instance, if we take a look at this first set of terms right here, so maybe I'll use my colors and use this set. What do we have? Well, the newtons, they're going to cancel. And then when I look at the meters, I have cubic meters divided by square meters. And so I'm just going to be left with meters. Plus, and then what do I have over here? Well, what do we have with this term? Well, the second squared cancel, and then I have meters squared over meter, just meter, plus meters. And so all these terms that added up, that had all these different sorts of units and all these different expressions, in the end, we were left with something that was dimensionally consistent. And so that's my answer. Sometimes when I do the problems on the board or on the homework assignment, I might just write A and S as a shorthand for answer. So is this problem dimensionally consistent? Yes, it is, because the three terms that I'm adding, they add up as meters, okay? And so there's really two ways you can look at a dimensional analysis problem. Either you're adding up terms that are all dimensionally consistent, or if you have an equation, you have one side of the equation and the other side of the equation, they have to equal the same unit system. And so on your homework assignment, that's what you're going to be looking at. Let me go ahead and go back to Collaborate. I'm going to stop the share. And let me share the, actually, I'm going to have to share the screen again. And then I'm going to have to stop. Sometimes Blackboard's a little quirky like that. Share files. Share the assignment. Okay, so here's the homework assignment that you are all going to have for this weekend, due Monday. And when you look at the expression, we have an equation, and we want to determine whether or not that expression is dimensionally consistent. And so I'm giving you an equation. This f times a quantity x2 minus x1 equals, 1/2 mv squared minus 1/2 mv squared. I want to know whether or not that's consistent. In other words, do what you get on the left-hand side of the equation, is it the same unit expression that you would get on the right-hand side of the equation? So either side of the equation, I want you to take those systems and plug and chug those units and perform that dimensional analysis to see if you get the same thing on the left that you do on the right. And you may not. I won't tell you the answer, but if you do that appropriately, you will. The one hint I'll give you is that One thing I didn't tell you is what is a Newton? How do you actually define a Newton? And if you go back to the previous lecture slides, you'll see the definition for the Newton in those slides. Okay. Now let's go to the meat of the lecture for today. All right, so that's our dimensional analysis. Again, pretty short, pretty straightforward. Let's look at our math review. Okay, I have here a somewhat funny meme here, but there's kind of a point that I want to make with the class. So I found this, online. I thought it was kind of funny that you have a professor that in the class the problems are and the examples and the homeworks are really easy, but then you start doing the work on your own and everything gets incredibly difficult. And I don't want that to be the case for this class, and I truly don't believe that statics is a science that's particularly difficult. It's a pretty straightforward concept and a pretty straightforward idea. However, one of the things that we are going to rely on a fair amount is math. We are going to be doing a fair amount of math in this class, and so I don't want the statics to get bogged down by some of the math that you haven't done in a while. For instance, I imagine that a fair amount of you probably haven't actually taken a trig class or an algebra class in a while. Most of you just took calculus and whatnot. And don't get me wrong, we will use calculus in this class. But some of this stuff, it might have been a while since you've looked at it. And so I want to review the mathematics that we're going to cover in this class. And this isn't going to be entirely comprehensive. I'm really going to focus on the trig. But I want to just make sure that everybody's familiar with some basic stuff. So let's start off. I only have one slide really on algebra. And the algebra that we perform in here is pretty straightforward. I have four, I would say, tasks that I think that you need to be familiar with. And some of them you don't really need to be familiar with right now. So they're not a focus of your homework assignment that you've got here in a bit. So first off, in terms of algebra, I think everybody needs to have a fairly basic understanding of just basics of operations. Make sure you can factor stuff and multiply stuff. Like for example, if you have A times the quantity B plus C, make sure you know that that's AB plus AC, that you have to distribute that out. As long as you can do that type of stuff, you're going to be fine in this class. It's also not a bad idea to understand the quadratic formula. We honestly might not use it all that much in the class, but it's, if you can work your way around the quadratic formula, you can work your way around a lot of the algebra that we'll be doing in this class. Two other things that are pretty important. So first off, in algebra, one of the big tasks that you learn is how to graph. What is a coordinate system? What is, the x-axis and the y-axis? I would say that's a fairly important concept to understand. I'm not saying that we're actually going to be doing a lot of graphing per se. I'm not going to be giving you equations and asking you to graph them, but we are going to be dealing with vectors, and without getting too much into the land, vectors are a way of expressing quantities in 2D and further even 3D space. And so understanding how coordinate systems work and what the axes represent, what how those operate are pretty important. And so you're going to want to understand that. Now, also what is going to show up later in the class is solving simultaneous equations. Now, before you get freaked out by this, if everybody in the class has a scientific calculator like a Casio FX, which most of you used in Engineering 111, or you have a TI 30 or 36, don't worry, the calculator will do a lot of this work for you. And don't get me wrong, this isn't a math class. I have no problem with you using those tools to solve those problems. But I do want you to just kind of have an understanding of what they mean. So for instance, if here's an example of a simultaneous equation. It's probably been a while since you've done these types of problems. I have two equations and two unknowns. I have 5x plus 3y equals 9, and then 2x minus 4y equals 14. So what are the magic values of x and y that satisfy both of those equations? And that's going to be very, very important to understand in this class, because we're actually going to be doing a fair number of these types of problems this semester. to give you a little bit of a taste of that. So we're talking about statics, okay? And statics is the principle of maintaining equilibrium of objects not really moving. Let's just say that we're talking about a stationary object. So let's say we're talking about an object let's just keep it simple, keep it in 2 dimensions. So I have an object in a plane, and I want to make sure it's not moving, or that it remains static. Well, in order for the object to remain static, I have 2 equations that have to be satisfied. The sum of forces in the x direction has to be equal to 0, and the sum of forces in the y direction, it has to be equal to 0. And so that's 2 equations, and with those 2 equations can naturally become 2 unknowns. And so we deal with these problems quite a bit. Now, a lot of times we find ways to work around having to actually solve the equations simultaneously, but it's something that you do need to be aware of. I'm not really getting super in depth on the algebra, because what's really important is the trig. Okay, I put one too many continued on the top of my slide, but that doesn't really matter. Let's talk about trig. Trig is something we're going to start using very quickly. The reason why is because, starting Monday, we're going to begin our definition and exploration of this concept called a vector. And vectors are, spoiler alert, vectors are the way that we represent forces in engineering mechanics. And so how you add forces, or how you add vectors, I should say, employs a lot of trig. And so we need to make sure that we're comfortable with this. And I know we're starting kind of basic with some of the stuff on the slide, but make sure you understand that if you have a triangle, that all the angles inside add up to 180 degrees, and that you know what complementary angles are. So if you have a 90, if you have 2 angles, if they're complementary, they add up to 90 degrees. If you have 2 angles and they're supplementary, they add up to 180 degrees. If you had 2 parallel lines and they're cut by a transversal, so for instance, like you see here on this slide, we know angles 1, 4, 5, and 8 are all equal, and angles 2, 3, 6, and 7 are all equal. This it's probably been a long time since you've looked at. But this is the type of stuff that we're going to be dealing with this semester. Now, one of the things I do want to point out about trig, we're not going to use all of it. For instance, you really won't find too many instances where we use radians. Probably really won't use it very much. We're talking about physical measurements of real-life systems, and so by and large we go with degrees. You probably won't see us use anything like a unit circle. Those concepts are incredibly important for explaining sine functions and cosine functions and all of that from a mathematical perspective, but from a user perspective and an analyst perspective for somebody taking statics, we really won't use that stuff that much. So when I put these slides together, I tried to make sure that we're focusing on the stuff that we're going to use this semester, the stuff that was applicable to your practice as engineers. So if we're talking about trig, we got to talk about 3 fundamental trig functions: sine, cosine, tangent. I don't think we're ever going to have an instance where we use the cosecant or the secant or the cotangent. That'll really never pop up. But sine, cosine, and tangent are going to be incredibly important. And basically what I'll say is this, is that one fundamental is that you kind of need to know your way around a right-hand or a right triangle. If I give you some data for a right triangle, you better be able to solve the rest of it. If I give you 2 sides, tell me what the hypotenuse is, tell me what the internal angles are, all that. Make sure the Pythagorean theorem. We're going to use the Pythagorean theorem a lot in the semester to determine lengths of vectors and all sorts of stuff. So that's just critical. Okay. In fact, one of your problems on your homework assignment is I give you some data about a right triangle, and you just need to solve the rest of it. I just need you to understand that. Okay. Another big one is while we won't directly convert between rectangular and polar coordinates, I think you do need to understand the relationship of the 2 of them. The first thing that we're going to do when we introduce vectors is we're kind of going to introduce them from a polar notation standpoint. We won't explicitly say, okay, this is polar notation, but it's going to be very indirectly leaning towards that direction. And then once we understand vectors from a polar coordinate or a polar notation standpoint, we'll then revert to a rectangular notation standpoint. If you go to the syllabus, you'll notice that in the schedule later on, there's this thing called IJK. And in fact, if you start flipping through your textbook, you'll start to see these IJKs kind of pop out at you. And IJKs are sort of a standard rectangular a coordinate system way of expressing vectors. And we'll get into the specifics of that later. But the long and short of it is kind of a relationship between polar and rectangular coordinates. So you won't really need to convert it per se, but you do need to understand it. Big one is being able to manipulate triangles in general. Now, sine, cosine, and tangent and your Pythagorean theorem are all you need to work your way around a right triangle. But we don't always deal with right triangles in engineering, and sometimes we have situations where we have stuff going all over the place. And so if sine, cosine, and tangent and your Pythagorean theorem is enough to solve a right triangle, if you have a scaling triangle, or if you have just an arbitrary triangle that you see here on the slide, you need a little bit more to assess the behavior, to solve for the remaining components of this triangle. And so what you really need are the law of sines, the law of cosines. It's probably been a while since you've looked at this, but basically the idea is this: you have a triangle, and a triangle is defined pretty much by 6 pieces of information. There's the 3 sides, the little a, little b, and little c. And then there's the 3 angles, the big A, the big B, and the big C. From a labeling perspective, we label that such that the angle and the side that have matching letters are opposite one another. So you can see, let me use my little pointer here. You can see this is angle A and this is side A, and they're opposite one another. Angle B, side B, C, side C. The law of sine states that the sine of angle A divided by A equals the sine of angle B divided by B, and the sine of angle C divided by C are all equivalent. And so, for instance, if I knew this angle, this side, and say this side, I could solve for this angle. And then let's say I knew angle A and angle B. Well, I could solve for angle C by just recognizing all the internal angles add up to 180 degrees. And then from that, I can either use the law of cosines or whatnot to go from there. Law of cosines works. Sometimes the law of cosines is referred to as the side angle side rule, because if you know, let's say, side B, side C, and angle A, you don't really have enough information to apply the law of sines, but you can apply the law of to determine the length of the other side. And so basically the law of cosines is just an expanded, more general expression for the Pythagorean theorem. If you look at this expression from a Pythagorean theorem standpoint, you have a squared equals b squared plus c squared minus 2bc cosine of a. Well, if a happens to be your right angle, this term goes to 0, and you're left with the Pythagorean theorem. So it's basically just a version of that. Incredibly important for solving triangles. I have a problem on your homework assignment dedicated explicitly to that. Okay. Last topic, calculus. Let's talk a little bit about calculus. And again, I threw continueds all over the place. I'll fix that on the slides that I uploaded. I built them and I threw continueds all over the place. I thought the slideshow was going to be longer than it was. Let's talk a little bit about calculus. First off, we're not really going to be doing any limits in this class, and the last thing that we're going to be dealing with is super complex derivatives, super complex integrals. That's not really the case. If you can handle pretty basic stuff, if you can handle a basic derivative and a basic integral, you're going to be good. I'm going to stop my screen share because I kind of want to show you where that's going to come into play. Okay, because one of the prerequisites of this class is calculus, and so I want you to have an understanding as to why you would use that. So I'll show you something. I have here just a plastic card. Okay, and so for the sake of discussion, let's say that this is a rectangle. Okay, now I have here, I don't know if you can see this on the screen, but it's a little push pin. Okay, now I'm probably not going to be able to do this on camera, but we'll see. So if I were to ask the question, where would I place this card on this pin in order to balance the card? And so, I don't know, maybe somewhere about right here, round in the middle, You know, I'm probably not going to be able to do the best job at this, but something about like that. Maybe I'll cheat a bit and do it on the other side where it's a bit flatter. There we go. So I'm putting the pen right pretty much in the middle of the card, and it balances. So for instance, if I were to take the pen and put it over here, it would just fall. Okay. The reason why is because I've balanced this object on what's called its centroid, or its center of gravity. You might have heard, you probably never heard the term centroid, but you probably heard the term center of gravity. And so if I place that object right on its centroid, oh, I got to place it on its centroid. Oh, I did it once, and now I've got to do it again, or it's going to bug me. Oh, maybe I've had too much coffee this morning. There we go. There we go. Place it on its centroid, and it balances. Okay. Now, it's easy for a rectangle. You know, if you have a rectangular shape, the centroid's right in the middle. That's easy. What about something like this? You know, this is what's called a French curve. If you've never seen this, we use this for when we're hand drafting something and we need a curve. You can face it all sorts of different ways, and it gets you, you know, the curve that you need. Where would I balance this? Well, I don't know about that. That one's kind of tough. Maybe it's like right here. Maybe it's over here. I don't know. But how would you determine that mathematically? Well, it involves calculus. It involves, you know, integration of the area in order to find a particular point. I don't want to get too much into the theory and too much into that idea. Basically, what you're trying to do is find the balance around what we call the first moment of area, but we'll talk about that later. But the point is to try and find where what we call the centroid of that location is, and there's a number of reasons why we need to determine that. There are relationships to the centroid with stuff you'll learn in later classes, like mechanics of materials. For instance, when you bend a beam, you cause stresses, but in bending, there are zero bending stresses at the centroid. And so there are a number of applications as to where that becomes important. And that's where calculus is gonna come into play. We'll probably do like a really brief calculus review when that stuff comes up, but it's not going to come up now. We've got a little bit of time before we have to deal with that stuff. Right now, what's going to come up is the trig. So I'm going to pull up the homework assignment. So here's the homework assignment, and what I've given you are two problems. Problem 2 is a right triangle, and problem 3 is a scaling triangle, and I've given you some data, and I just want you to solve for the rest of the triangle. So in problem 2, I gave you one of the angles and one of the sides. I want you to give me the other two sides and the other angle. Obviously, angle C is 90 degrees. You don't have to give me that one. Problem 3, I've given you two of the sides and one of the angles. Give me everything else. And so I have here for problem 3 to use either the law of sines or the law of cosines to figure everything else out. In terms of reporting your answer, just 2 decimal places is fine. I don't really get too worked up with significant figures on this. Really, I just want to make sure that everybody's clear on the trig and understanding that, because starting Monday, we're really going to start to dig into the aspect of vectors. And when I start adding vectors up, I'm going to be using trig, and I don't want everybody to go, oh God, it's been a while since we've done this. That's the whole point of this assignment, is to shake the rust off, if you will, on the trig. So that'll be due Monday at 1 p.m. Don't forget to turn in your homework today that's due 1 p.m. And that's pretty much all for my lecture. I hope everybody has a good weekend. Everybody stay safe and healthy, and we'll see you next week.